Hi everyone, welcome once more to this YouTube channel at Best Science Brain YouTube. Today we're looking at another topic in general chemistry known as stoichiometry of reactions. This topic is very important because it helps you to understand the relationship between the reactants and products in a chemical reaction. After this topic, you'll be able to calculate the mass of reactant involved in a given reaction, mass of product formed in a given reaction, volume of reactant involved in a reaction, or volume of product or gaseous product produced in a given reaction. If you're not subscribed to the channel, move up now to the channel's name, Best Science Brain, that's the channel's name. Under the channel's name, you see a subscription icon or button. Tap on the subscription only once and get subscribed to the channel for more tutorial videos in general chemistry and also general physics. So, looking at this topic, the word stoichiometry. The word stoichiometry, pronounced stoichiometry, is derived from the Greek word stoichion. Stoichion meaning element, and metron meaning measure. So that word comes from two Greek words, stoichion and metron, meaning element and measure. So in chemistry, stoichiometry is the study of the quantitative relationship between the amounts of reactants and products and its guiding principle. It is based on the mole concept. So as I explained, in stoichiometry, we're interested in knowing the amount of reactant involved in a reaction and the amount of product formed in a given reaction. Okay, we'll now go over to what is meant by stoichiometric coefficient. Stoichiometric coefficient. We're going to explain this first by considering a mathematical equation. You see, let us consider the mathematical equation given below. We have 2s plus 5z giving us 4y plus 7m. Now, this coefficient of s is the number in front of s, which is 2. Coefficient of z is 5. Coefficient of y is 4. And then coefficient of m is 7. So it reads in the above mathematical equation, the coefficient of s, y, sz, y, and m are 2, 5, 4, and 7 respectively, as you can see in the equation. So we now understand what is meant by coefficient. Now we're going to relate this to balance equation. So we now move in a balance chemical equation. The stoichiometric ratios are the number of moles of the reactants and products as they appear in the balance equation. So let us consider the example given below. So look at that chemical equation between magnesium and oxygen. Magnesium was bound in oxygen, give us magnesium oxide. 2 moles of magnesium, 1 mole of oxygen molecule, and 2 moles of magnesium oxide. So in a similar manner, the numbers in front of the reactants, that is 2 moles of magnesium, 1 mole of oxygen, and 2 moles of magnesium oxide, stand for the stoichiometric coefficients. So if you relate it to mathematical equation, the numbers in front of the variables s, z, y, and m are the coefficients. So in a balanced equation, the numbers in front of the substances also represent what we call the stoichiometric coefficients. So it reads, from the above balanced equation, we can comfortably say 2 moles of magnesium reacted with 1 mole of oxygen molecule to produce 2 moles of magnesium oxide. You can see that magnesium and oxygen are reactants, and magnesium oxide is a product. So we can say 2 moles of magnesium reacted with 1 mole of oxygen to produce 2 moles of magnesium oxide. Again, from a tutorial on mole concept. So if you have not watched the video on mole concept, that is introduction to stoichiometry, mole concept, you check for it in this YouTube channel, and then be able to download it and then be able to study it. Again, from our tutorial on mole concept, we made it clear that 1 mole of a metal is equal to its relative atomic mass. Yes, a metal, 1 mole of a metal corresponds to its relative atomic mass because a metal is monatomic. For instance, look at that equation. Magnesium is a metal. So if you look at magnesium, it's written Mg. It's not written as Mg2. So it's not Mg2, like unlike oxygen, which is O2. So metals are written as monatomic elements. So 1 mole of magnesium is equal to the atomic mass of magnesium. But for oxygen is diatomic, O2. So 1 mole of oxygen will not be equal to the molecular mass of oxygen. And then MgO is a compound. So 1 mole of MgO is equal to the molar mass of a compound. Since a monatomic element is classified by its relative atomic mass, while a diatomic substance like oxygen is classified using its molecular mass, and a compound is classified using its molar mass. So let's go on. Relative atomic mass of magnesium is 24. Hence, 1 mole of magnesium weighs 24 grams. So atomic mass of magnesium is 24. 1 mole of magnesium is 24 grams. Because magnesium is a metal, being monatomic. Similarly, 1 mole of a molecule is relative molecular mass. The relative molecular mass of oxygen is relative atomic mass of oxygen is 16. But oxygen exists as a molecule, know that. Hence, the relative molecular mass of oxygen is given by O2, which is 16 times 2. 16 stands for the mass of an atom. So since there are 2 atoms in a molecule, so the molecular mass or the molar mass also is 16 times 2. That gives us 32. So consequently, 1 mole of oxygen molecule weighs 32 grams. So for a molecule, 1 mole of it is equal to the molecular mass or molar mass. The product of the reaction is magnesium oxide, as I explained before. 1 mole of a compound is its molar mass. The molar mass of MgO is obtained below. You get the molar mass by adding the atomic masses. Atomic mass of magnesium plus atomic mass of oxygen, which is 24 plus 16, giving us 40 grams per mole. So 1 mole of magnesium is equal to the molar mass. So 1 mole of magnesium will now give us 40 grams. Now let's relate all these values to the above balanced equation. Look at the equation written down there. So how to convert those moles to masses? So now I see from the balanced equation, we have 2 moles of magnesium, 1 mole of oxygen, and 2 moles of magnesium oxide. Since 1 mole of a metal is equal to atomic mass, so 2 moles of magnesium becomes 2 times 24, and that will give us 48 grams. Since 1 mole of a molecule is equal to molecular mass, 32, so we have 1 mole there, which is equivalent to 32 grams underneath. Now, 1 mole of a compound, MgO, is equal to the molar mass. The molar mass of MgO, which I calculated above, is 40 grams. So 2 moles now become 2 times 40, that gives us 80 grams. So you see, converting the mole to masses. So far, so good. So we can comfortably say that 48 grams of magnesium reacted with 32 grams of oxygen to produce 80 grams of magnesium oxide. So that's what we have here. We can also comfortably say that 48 grams of magnesium reacted with 2 grams of oxygen to produce 80 grams of magnesium oxide. Having understood this, we take another example. Look at that equation between HCl, sodium carbonate, to give us sodium chloride, carbon 4 oxide, and oxygen. Now, the stoichiometric number of moles are the numbers or the coefficients in front of the substances, number used to balance the equation. So we can say that 2 moles of HCl reacted with 1 mole of sodium carbonate to produce 2 moles of sodium chloride, 1 mole of carbon 4 oxide, and 1 mole of water. Then, that is it. We can now say, in order to relate the stoichiometric number of moles to the masses, what do? We have to calculate the molar mass of each element, or of each reactant, each compound and product in the balanced equation. Remember, we say that the molar mass of a compound is equal to 1 mole of a compound is equal to its molar mass. So to calculate the molar mass of the compound, we need the relative atomic masses of the elements in the reaction: hydrogen, chlorine, sodium, carbon, and oxygen. The other atomic masses include 1 for hydrogen, 5.5 for chlorine, 23 for sodium, 12 for carbon, and 16 for oxygen respectively. And these are used to calculate the molar masses as emphasized previously. So when I look at how to find the molar masses of the compounds, we look at the column for reactants. Reactants here are from the balance equation. Reactants are HCl and sodium carbonate. To find the molar mass of HCl, we now say 1 plus 35.5. That gives us 36.5 gram per mole. Then to find the molar mass of sodium carbonate, we have 23, which is the mass of one atom of sodium, times 2, because there are 2 atoms of sodium there, plus carbon, the atom mass of carbon is 12, plus oxygen, the atom mass is 16, but multiplied by 3, since there are 3 atoms of oxygen in the compound. So 2 times 3, 23 is 46, 46 plus 12 will give us 58. Then 3 times 16 is 48. So 48 plus 58 give us 106. The molar mass of sodium carbonate is 106. We now go to the products. The products in the reaction are NaCl, CO2, and water. We find the molar mass of NaCl, sodium is 23, chlorate at 5.5. Adding the two, we have 58.5 grams per mole. Find the molar mass of CO2, carbon is 12, oxygen is 16, but multiplied by 2 because of 2 atoms in CO2. We will now have 12 plus 32 giving us 44 grams per mole. Find the molar mass of water. We will now have 2 times 1. Hydrogen, atomic mass of hydrogen is 1. Multiplied by 2, since we have 2 atoms, plus 16. That 16 is for oxygen, giving us 18 grams per mole. So we now say, now converting the stoichiometric moles in the balance equation to masses, we have, you see that we have 2 moles of HCl. The molar mass of HCl is 36.5, as we saw on the table above. 36.5. So, and that molar mass means the mass of 1 mole. So 2 moles becomes 2 times 36.5, as you have the equation, giving us 73 grams. The molar mass of sodium carbonate is 106 calculated, and there's only 1 mole there in the balance equation. So 1 mole is what 106, that's the molar mass. The molar mass of sodium chloride is 58.5, as we did above, 58.5. Okay, but there are 2 moles in the balance equation. We now have 58.5 times 2, giving us 119 gram. The molar mass of CO2 is 44 gram. So there's only 1 mole there. That means that 1 mole of CO2 is 44 grams. The molar mass of water is 18 grams. So, and there's 1 mole of water in the equation, and that corresponds to 18 grams. So it is right for us to say that 73 grams of HCl reacted with 106 grams of sodium carbonate to produce 119 grams of sodium chloride and 44 grams of CO2 and 18 grams of water. So that's the expression we have there. Say, from the above equation, we can as well say 73 grams of HCl reacted with 106 grams of sodium carbonate to produce 119 grams of sodium chloride, 44 grams of CO2, and 18 grams of water. So, how do we tackle stoichiometric problems involving balance equations? So, how do we solve mathematical problems that involve reactions or balance equations? So, we say there is no general format for tackling stoichiometric problems. However, the above steps can help us in this video. So we don't have a general way of tackling problems involving equations, but there are some concepts or some procedure that will help us, or some steps that will help us. The first step is that we have to understand the mole concept as explained above, and our previous videos on introductory stoichiometry. So we have to have an idea or how to explain or how to equate reactants in terms of mole concept as I explained above. Then the second step is that if the chemical reaction equation is not provided, because sometimes we're given a problem whereby there is no chemical equation, but as long as there's a reaction, you must write the chemical equation and balance it. If the chemical equation is not provided, then you must write a balanced equation for the reaction. Note that a wrong equation or an unbalanced equation will always lead to failure. So if you don't have a balanced equation or you don't have an equation at all, you must write an equation for the reaction provided there's a reaction. Provided the reaction, there must be a chemical equation before you start solving it. Then relate only two substances at a time. So when you're solving, you have to connect only two substances at a time. You don't have to relate all the substances to the balanced equation. You only relate two substances at a time. Only relate the known to the unknown. What I call the known to the unknown. What do I mean by the known? The known or the known substance is the substance whose value is given to you. And the value is given to you could be amount, mass, or concentration is given to you in the question. So I say the known is the substance whose amount, mass, or concentration is provided in the question. That is called the known, so because you know the quantity given to you about that substance. While the unknown is the substance you are calculating its quantity. So the one you have to calculate, whether you have to calculate its mass, its volume, or its concentration is now your unknown. You only connect two substances. You don't have to connect all the substances in the balanced equation. You're only concerned with only two in solving such problem. And then the third step says, solve the problem by using the mole concept or by converting the stoichiometric moles to masses, as have been taught above. When I look at exercise 1, an example of how to apply the stoichiometric relationship, says 20.0 gram of limestone was thermally decomposed by heat. A. Write a balanced equation, chemical equation for the reaction. B. Calculate the number of moles of quicklime produced. In bracket, you're given the atoms of calcium as 40, the atoms of carbon as 12, and oxygen as 16. So we are asked to first of all write the equation for the reaction. We'll go to the solution. Look at the equation. Limestone is calcium carbonate. And then it decomposes into calcium oxide, which is known as quicklime, and CO2. So that's the balanced equation. If you look at the equation, that's number A, we have to bold two substances there. We made the letters bold. That is calcium carbonate and calcium oxide. We are made bold. While CO2 was left without making it bold. So why do we make calcium carbonate and calcium oxide bold? The letters there we are made bold because one of them is the known, one of them is the unknown. Which one is the known? If you go to the equation, they gave us 20 grams. The limestone mass was provided for you. So since they gave us the quantity of limestone, the limestone becomes the known substance, the one whose quantity is already known. While calcium oxide is the unknown. Why is it unknown? Because we asked in question B, find the number of moles of quicklime. Quicklime is calcium oxide, so that's the one we're looking for. So we only connect calcium carbonate to calcium oxide, limestone, calcium carbonate, and then quicklime, calcium oxide. That's why question mark is on calcium oxide is unknown. We have no business with CO2 in this question, but we're not asked to find anything about CO2. So we'll start by stating our work. Mass of calcium carbonate or limestone, M, is 20 grams. Then we'll find the molar mass of the calcium carbonate by adding that to masses of calcium 40 plus carbon 12 plus oxygen 16 multiplied by 3 because of the 3 atoms in the carbonate. And that'll give us 100 grams per mole. We'll now find the number of moles of calcium carbonate, that the known substance participating in the reaction. Since we're given mass, so the connection between mass and number of moles is mass over molar mass. So mole of calcium carbonate becomes 20 over 100, making substitution. That gives us 0.20 mole of calcium carbonate. Now we'll connect the known, that is calcium carbonate, to the unknown, quicklime, calcium oxide, in the balanced equation. If you look at the balanced equation, you see that the number of moles of each of them is 1:1, 1 mole to 1 mole. So we'll now move on and say 1 mole of calcium carbonate is equal to 1 mole of calcium oxide. Therefore, 0.20 mole of calcium carbonate. the first statement, 1 mole of calcium carbonate is equal to 1 mole of calcium oxide that came from the balance equation. Therefore, 0.20. Why did I get 0.20? 0.20 is the reacting mole of carbonate that was calculated, the actual mole that is participating in the chemical reaction. So 0.2 mole of calcium carbonate will now produce the same 0.20 mole of calcium because the ratio is 1:1. So 0.2 of this will still give you 0.20 mole of calcium oxide. Had it been that the ratio is 1:2, so 0.2 would have been 0.2 times 2. So the number of moles of quicklime produced is 0.2 mole of calcium oxide or quicklime produced. So that's the answer to this simple question. Then we have another method 2 for solving it. Method 2 now is that we're going to convert this mole, 1 mole of carbonate and 1 mole to masses. So method 2, in this method, we need to understand that 1 mole of a compound is equal to its molar mass. Thus, we have to first calculate the molar mass of the known substance, calcium carbonate, and that of the unknown substance, calcium oxide. So molar mass of calcium carbonate is calculated as it has been done before, 40 plus 12. These atomic masses of calcium carbon given to you in bracket. Also is 16 times 3, giving us 100 grams per mole. Then that is for the known substance. The unknown that we're looking for, we find the molar mass, 40 plus 16, that gives us 56 grams per mole. We now have the equation. We're looking for calcium oxide. The question mark is on it. And then we're giving calcium carbonate. And the mole ratio, the stoichiometric mole ratio is 1:1, 1 mole to 1 mole. So when I say connecting calcium carbonate to calcium oxide in the balance equation, when I have 1 mole of calcium carbonate give 1 mole of calcium oxide, as you can see there. And we know in chemistry that 1 mole of a compound is equal to the molar mass. To replace 1 mole of calcium carbonate with 100 grams, which is the molar mass of calcium carbonate. They replace 1 mole of calcium oxide with 56 grams, which is its molar mass. So 100 grams of calcium carbonate gave us 56 grams of calcium oxide. Therefore, 20 grams of the carbonate, 20 grams is the mass provided in the equation. 20 grams of calcium carbonate will give us 20 times 56 over 100 by working by proportion. We now have 11.2 grams of calcium oxide produced. Then mole of calcium oxide. Since we're looking for mole, not mass, we need to convert this mass of calcium oxide, which is quicklime, to mole. So you know that mole is mass over molar mass. So the mass of calcium oxide produced is 11.2. The molar mass of calcium oxide, which I've calculated before, is 56. When I have 11.2 over 56, that gives us the same 0.20 mole of calcium oxide or quicklime produced. So we'll go to the second question that says, exercise 2. Calculate the mass of lead 2 chloride that would be precipitated when 16.6 grams of lead 2 triiodonitrate 5 reacts with excess sodium chloride according to the equation below. Calculate the mass of lead 2 chloride that would be precipitated when 16.6 grams of lead 2 triiodonitrate 5 reacts with excess sodium chloride according to the equation below. And they gave us atomic mass of lead as 207, nitrogen as 14, oxygen as 16. And then we are lucky that they gave us the balance equation between lead nitrate, sodium chloride, give us lead 2 chloride, and then sodium nitrate. So we look at method 1. The equation for the reaction is given to us already. So we'll have the equation written down again. Then what are we looking for? We have asked to find the mass of lead 2 chloride. That's why the question mark is on it. And lead 2 chloride was also made bold. So that's what we're looking for. Then which substance are we going to use to connect to lead 2 chloride? We're going to connect it to lead nitrate also because they gave us the mass of lead nitrate in the equation. So the mass of lead nitrate was given to us. So let's check it out. The mass of lead nitrate is 16.6 grams of lead nitrate. So it's known why lead chloride is what we're looking for. So that's the reason for that. So as we say, when you have this situation, find the molar masses of the known and the unknown. So the molar mass of lead nitrate calculated, lead is 207, bracket opens, nitrogen is 14 plus 14, then bracket plus again, also is 16, multiplied by 3 because there are 3 atoms of oxygen. Then close the bracket and multiply by the 2 that's outside the bracket. We now have 207 plus, If you solve out the bracket, what is inside the bracket? 14. 3 times 16 is 48. 48 plus 14 gives you 62. Then multiply by the 2 outside. You now have that. So we now have 207 plus 124, giving us 331 gram per mole. So this is the molar mass of lead nitrate. Then you find the molar mass of lead 2 chloride. There, lead is 207, chlorine is at 5.5, multiplied by 2 because of 2 atoms there. That gives us 207 plus 71, and that will give us 271 gram per mole. That's the mass of 1 mole of lead chloride. So, connecting from the balance equation, lead nitrate, the known substance, to lead chloride or non-substance. So, you see, lead nitrate, you have 1 mole of lead nitrate and 1 mole of lead 2 chloride. So you connect the two of them. 1 mole of lead nitrate equal to 1 mole of lead 2 chloride. Then you know that the 1 mole of a substance is equal to the molar mass. So now I say 331 gram of lead nitrate produce 1 mole of lead chloride, which is the molar mass also 278. Replace the mole by the molar masses. Therefore, 16.6 gram, with the mass of lead nitrate given in the question, we now produce 16.6 times 278 all over 331. By proportion, we get 13.9 gram of lead 2 chloride. Now, method 2, using the mole concept. In this method 2, we have to convert the mass given to us to mole. Mass of lead nitrate is 16.6. That's the known substance. The molar mass of lead nitrate have been calculated before us in the first example as 331 gram per mole. So we have to change the mass to mole. Mole of lead nitrate is mass over molar mass, which is 16.6 all over 331. That gives us 0.0502 mole of lead nitrate in the reaction. We now connect from the balance equation as we did before. The number of moles in the equation is 1:1. So 1 mole of lead nitrate is equivalent to 1 mole of lead chloride. 0.0502 mole, which is the number of moles obtained, reactive mole obtained by calculation of lead nitrate, give us also the same 0.0502 mole of lead chloride, because the ratio is 1:1. So S mole of this will still give the same S mole of that. So the molar mass of lead 2 chloride have been calculated before as 278 grams 278 grams per mole. But since we're looking for mass, we have to change this 0.05 mole of lead chloride to mass, using mass equal to mole times molar mass, which is going to be 0.0502 times 278. And we'll still get the same 13.9 grams of lead 2 chloride, the same value, the same answer. Okay, going to exercise 3. Exercise 3 says 18.5 gram of potassium chloride was produced when some potassium triazo chloride 5 crystals were decomposed by heat according to the equation below. So we are given the equation. And if you look at the equation, they gave us 18.5 gram of product, potassium chloride was produced. Okay, so the known substance now is the product. We know the mass of one of the products. Then there's also determine the mass of potassium triazochloride 5 that was decomposed. We're looking for mass of the reactant. We are now connecting the product to the reactant. The known is the product, 18.5 gram of potassium chloride. The unknown is the reactant, which is potassium chloride or triazochloride 5. You can see the equation again. 18.5 gram of potassium chloride was produced when some potassium chloride 5 crystals were decomposed. So we have that mass of potassium there, 39, chlorine 35.5, oxygen equal to 6. The equation is provided for us already, so we'll have it written out again. Then we made 2 substances bold there, KClO3, potassium triazochloride, and KCl. 2 of them were made bold. Then the question mark is on the unknown potassium, the reactant is unknown. Potassium triazochloride 5 is the unknown substance. So that is the reactant. Why the mass of the potassium chloride was given to us as 18.5. So let's go on. The mass of the potassium chloride, that's M stand for mass, provided is 18.5 gram. We'll find its molar mass by adding the atomic mass of potassium is 39 and chloride 5.5, and that gives us 74.5 gram per mole. Then the molar mass of the known substance, which is KClO3, is calculated. Potassium is 39, chlorine 35.5, oxygen is 16 multiplied by 3 because of 3 atoms there. If you add everything together, you're going to have 122.5 gram per mole. Then we're going to connect the two substances, connecting KCl to KC. We'll start from the known, KCl to KClO3. Not mind whether KClO3 is the reactant or not. We'll start from the known and move to the unknown. But you look at the equation, the stoichiometric ratio is 2 is to 2, 2 moles to 2 moles. So move and say 2 moles of KCl is equivalent to 2 moles of KClO3. And we're going to convert this mole to masses as well. Calculate the molar mass of KCl as 4.5. So 2 moles is giving us 1 mole of KCl, that the molar mass is 4.5. And we'll have 2 moles in the balance equation. Now I'm applying. If 1 mole is 4.5, that's the molar mass, then 2 mole becomes 2 times 4.5. That gives us 149 grams. Then the molar mass of KClO3 is 122.5. So if 1 mole is the molar mass is 122.5, 2 moles in the equation now become 2 times 122.5, giving us 245 grams. So that one will have 149 grams of KCl, giving us 245 grams of KClO3. Therefore, 18.5 grams. 18.5 grams is the mass of potassium chloride produced that is given in the equation. Will now give us 18.5 times 245 over 149. By proportion, we'll have 30.4 grams of potassium chloride. So 30.4 grams of potassium chloride was able to produce 18.5 grams of potassium chloride. So having done that, we go to question exercise 4. Propane C3 hydrocarbon C3H8 can be used as fuel in car because it is easily liquefied and transported. If 454 grams of propane was completely burnt, calculate the A, mass of oxygen required for combustion, B, mass of CO2 produced, C, mass of steam produced, D, volume of CO2 evolved at STP. And in bracket, we're given atoms of carbon as 12, hydrogen as 1, oxygen as 16, and then 1 mole of a gas occupies 2.4 dN cube at STP, with the molar volume of gas at STP. So go to the solution. In the solution, first, we need to write a balanced chemical equation for the reaction. We need to write a balanced equation for the reaction. The reactants are propane and oxygen because we are told that propane was burnt. So that's the combustion reaction. If propane was burnt, it means that propane combined with oxygen. So look at it. Propane can be used as fuel in car because it is liquefied and transported. If 454 grams of propane was completely burnt, so that means that reaction is combustion, propane combined with oxygen. And whenever a hydrocarbon burns with oxygen, it's going to produce only 2 products. The 2 products are CO2 and steam. So they say the reactants are propane and oxygen. Propane is a hydrocarbon, and all hydrocarbons burn completely in oxygen to give CO2 and steam. Hydrocarbons are compounds that contain only carbon and hydrogen. So you have the equation and it's well balanced. If it's not balanced, it's not making any sense at all. So look at the question A. Question A says we should find the mass of oxygen produced. Mass of oxygen produced. So we'll start. Now we made propane bold and make oxygen bold. Why? Propane is the known because the mass was given to us. Look at the mass of propane in the equation. We're given to us as 454 grams. And we're looking for the mass of oxygen, that's the unknown. So we connected the 2 of them, made them bold. We don't have business with CO2 and steam now. So we only connect 2 substances as I said earlier on in this video. Then mass of oxygen is unknown. So having done that, that's why you have question mark on top of oxygen. We'll find the molar mass of propane, which is carbon is 12 multiplied by 3 atoms there. Hydrogen is 1 multiplied by 8, equal to the 8 atoms. We're going to have 44 grams per mole. That's the molar mass of propane. For oxygen, we have 16 times 2 because atom mass of oxygen is 16 and is a molecule times 2. That is 32 grams. The molar mass of oxygen is 32 grams per mole. They will go to balance equation and connect them together. 1 mole of propane to 5 moles of oxygen. We now say connecting propane to oxygen in the balance equation. 1 mole of propane giving us 5 moles of oxygen. We now convert these moles to masses. 1 mole of propane is equal to the molar mass, which is 44 grams of propane. 5 moles of oxygen is equal to 5 times the molar mass. Since the molar mass of oxygen is 32, so you see there's an error in the calculation there. We'll have to correct the error. Instead of 16 here should be 32, not 16. 32 grams of oxygen. So multiply. There should give us 160, not 80. 160 grams of oxygen. So we'll go ahead. 44 grams of propane combined with 160 grams of oxygen. Remember that oxygen is a molecule. So that was an error, which is the molar mass is 32, not 16. So, and 1 mole of a molecule is equal to the molar mass. You have 5 moles there. It's going to be 5 times 32, not 5 times 16. So 454 now give us, okay, 44 grams of propane reacted with or combined with 160 grams of oxygen. Therefore, 454, which is given to us in the balance equation, the mass of propane that is reacted is 454 grams. That was burnt is 54 grams. So 44 grams will now combine with, we change that 80 to 160. We'll combine with, change to 160. So the answer will be times 2 of this. So you can work it out. Times 2 of that. So that'll be the answer to get the mass of oxygen gas that was produced. So if you multiply it, you can get the answer 0. We're going to have 0, 5, 6, that's 1650. That should be around that. So we're going to have 16650 grams of oxygen. So look at it. Let's be sure of the answer. 2 times 5 is 0, carry 1. 2 times 5 is 0 again. Plus 1 is 1. Okay, I did an error there. 2 times 5 is 0, carry 1. 2 times 5 is 0. And that'll give you 1 here. 1 there. 2 times 5 is 0. 10 plus 11, carry 1, 2 times 2, 4, plus 1, 5. So you're going to have 1,651 grams of oxygen. 1,651 grams of oxygen produced. Error corrected, please. So that is it. We'll go to question 2. Question B. We are asked to find the mass of carbon dioxide produced from the same reaction between propane and oxygen. So the mass of carbon dioxide produced. Propane remains the known substance because the mass of propane, which is 454 grams, was given to us in the question. While now the unknown is no longer oxygen, the unknown is now carbon dioxide, which we're looking for. Now we'll have question mark on carbon dioxide, CO2. There's a question mark on it. So we're looking for the mass of carbon dioxide, as you can see there. Question mark is on it. Then we'll find the molar mass of the known substance propane, which have been done before. 3 times 12. That is 3 atoms of carbon times 12. 2 moles of carbon is 12. Hydrogen is 8 times 1. 8 atoms times 1, giving us 44 grams per mole. And the molar mass of the unknown substance, one we're looking for is CO2. Find its molar mass also. We have carbon is 12, atoms of carbon is 12, oxygen is 16 times 2, that is 32 plus 2, again now 44 grams per mole. We'll now move from the balance equation, we'll connect the two substances. We'll see that 1 mole of propane gave 3 moles of carbon dioxide. So we'll now say 1 mole of propane equal to 3 moles of CO2. And 1 mole of a compound, as we say, is equal to the molar mass. So replace the 1 mole with 44 grams of propane, and then 1 mole of CO2 is the molar mass, which is 44 grams per mole. But in the equation, reaction will have 3 moles. Multiply 44 by 3 because of 3 moles. So if 1 mole is 44 grams, then 3 moles will be 3 times 44. So we'll have 132 grams. So we'll have 44 grams of propane gave us 132 grams of CO2. Therefore, 454 grams of propane given to us in the equation that was burnt will now give us 454 times 132 over 44. And that will give us 1,362 grams of CO2. Going to question C, we are asked to find the mass of steam produced in the reaction. So you see that our arrow sheet from CO2 now to steam. Steam is the unknown. Question mark is on steam. We still connect propane, whose mass is given to us, the known, to steam, which we are looking for. The mass of propane is 454, given to us in the equation. Mass of steam is unknown. Molar mass of propane have been calculated before, 44 grams per mole. We find the molar mass of steam, which is 2 times 1 for hydrogen atom is 2. The atom mass of hydrogen is 1. Then plus oxygen, the atom mass of oxygen is 16. That gives us 18 grams per mole. Then we'll connect from the balance equation, connect steam to CO2. We connect propane to steam. 1 more propane to 4 moles of steam. We go down. 1 more propane, C3H4, H8, gave us what 4 moles of steam from the balance equation. And 1 more propane is equal to the molar mass, 44 grams. 4 moles of steam, the molar mass of steam is equal to 1 mole, that's 18 grams, but there are 4 moles there multiplied by 4 to find the weight of 4 moles. So 44 grams of propane gave us 72 grams of steam. 4 times 80 is 72. Then therefore 454 grams of propane, which is the mass of propane, burnt will give us 454 times 72 all over 44 by proportion, and that will give us 743 grams of steam. We go to question D. Question D, we are asked to find the volume of CO2 gas liberated at STP. We connect propane back to CO2. Question mark is on CO2, so we're looking for CO2. Mass of propane is 454 grams that was burnt. We're looking for the volume of CO2. We'll find the molar mass of propane, which have been done several times here, that 44 grams per mole. We'll now connect propane to CO2 for the balance equation. You see that in this equation, 1 more propane leads to 3 moles of CO2. So we'll move on and say 1 more propane, give us 3 moles of CO2. 44 grams of propane. 44 grams represents the molar mass, which is equivalent to 1 mole of propane. Gave us, we don't have to find the mass of CO2 here because we're looking for the volume of CO2. So we'll convert 3 moles of CO2 to volume. And you know that 1 mole of a gas at STP is 22.4 dN cube. So 3 moles of a gas is now 3 times 22.4. So that 22.4 is given to you in brackets, a constant. 1 mole of every gas occupies 22.4 dN cube at standard temperature and pressure. So since I have 3 moles here, I have 3 times 22.4, that gives me 67.2 dN cube. So therefore, 454 grams of propane that was burnt will now provide 454 times 67.2 dN cube all over 44, and that give me 693.4 dN cube of carbon 4 oxide. We look at exercise 5. Exercise 5 says 2.56 grams of aluminium reacts with bromine according to the equation below. How many grams of the aluminium bromide will be produced? 2.56 grams of aluminium reacts with bromine according to the equation below. How many grams of the aluminium bromide will be produced? So we are given that equation between aluminium and bromine to produce 2 moles of aluminium and 3 moles of bromine to give us 1 mole of the aluminium bromide. So in this question, now we're looking for the mass of the aluminium bromide produced. You see, it was made bold, and question mark is on it, the product. And they were connecting to aluminium. Aluminium is made bold because they give out the mass of aluminium. So aluminium is the known substance here now, while the aluminium bromide is the unknown substance. So mass of aluminium that reacted is 2.56 grams. Aluminium is a metal, and metals are monatomic. So the atomic mass of aluminium is 27, and that represents the weight of 1 mole of aluminium. Then the mass of aluminium dibromide, what we're looking for. The aluminium bromide is what we're looking for. We'll have to find the molar mass of also the aluminium bromide. Aluminium is 27 in bracket, given to you already, times 2 atoms, because of the 2 atoms there, plus bromine is 80 times 6. The atomic mass of bromine is 80 times 6, because of 6 atoms there. If you add everything together, 54 plus 480, we get 534 grams per mole. So you can see the equation. You're given the atomic mass of aluminium and bromine already, so that what to use in calculating the molar mass of the aluminium bromide. Then we'll connect the 2 substances in the equation. We'll have 2 moles of aluminium and 1 mole of the aluminium bromide. So we'll move on and say 2 moles of aluminium equivalent to 1 mole of the aluminum bromide. Then you know that 1 mole of aluminum being a metal is equal to atomic mass. So the atomic mass is 27. So 2 moles will now become 2 times 27. That is 54 grams of aluminum. 1 mole of aluminum, the aluminum bromide is 534. That's the molar mass. So we change that to 1 mole of that compound to 534 grams of the aluminum dibromide. So we have that. Then therefore 2.56 gram aluminum, because 2.56 is the mass of aluminum that is involved in the reaction given to you in the equation. 2.56 gram of aluminum will now give us 2.56 multiplied by 534 all over 54 grams. So we'll now work it out. We'll now have 25.3 grams of the aluminum bromide as our product. So exercise 6 says iron ore is reduced to carbon 2 oxide. It reduced by carbon 2 oxide to its metal as shown below. So we have an equation between iron ore, that iron 3 oxide and carbon 2 oxide, giving us iron and carbon 4 oxide. And we ask how many grams of carbon 2 oxide are required to consume completely 36.5 grams of iron ore or iron 3 oxide. The first question, the second question says how many kilograms of iron 3 oxide are required to produce 27.9 kilogram of iron, and they gave us atoms of iron as 56, oxygen as 16, carbon as 12. Solution. So how do we solve this problem? The balance equation given to us. So the mass of iron oxide in the first question was given to us as 6.5 gram was given provided for us. So iron oxide or the iron ore is the known substance. But we're looking for the mass of carbon 2 oxide, which is unknown. That's why you have a question mark on it. The two substances were made bold. So having done that, we find the molar mass or molecular mass of iron 2 oxide. It's been the known substance. We'll now use the atoms of iron in bracket is 56 times 2 because of there are 2 atoms of iron there, plus atoms of oxygen is 16 given to you in bracket times 3 because of there are 3 atoms of oxygen there. You have 112 plus 48. If you open the bracket, you have 160 grams per mole as the molar mass of iron 3 oxide, the iron ore. But we're looking for the mass of carbon 2 oxide. We have to find the molar mass of carbon 2 oxide first. The molar mass of carbon 2 oxide is obtained by adding the mass of carbon to oxygen. The atomic mass of carbon to oxygen is 12 plus 16, giving us 28 grams per mole. Then work from the balance equation. Look at the two substances and connect the known iron oxide to the unknown carbon 2 oxide. 1 mole of iron oxide or iron ore to 3 moles of carbon 2 oxide. So we now say connecting iron 3 oxide to CO, the balance equation. We now have 1 mole of iron 3 oxide or iron ore to 3 moles of carbon 2 oxide. And you know that 1 mole of a substance is molar mass. So changing the 1 mole to 160 grams of iron 3 oxide. Then for carbon 2 oxide, the molar mass is 28. But since there are 3 moles, we apply 28 by 3. We go down, we have 160 grams of iron oxide, give us 84 grams of carbon 2 oxide. Therefore, that's 6.5 grams, which is the mass of iron oxide given to us in the equation of iron oxide or iron ore will give us that 6.5 times 84 over 160, and that will give you 19.2 grams of the aluminum bromide produced in the reaction. The B equation, the B says we should, how many kilograms of iron 3 oxide are required to produce 27.9 how many kilograms of iron oxide, iron 3 oxide are required to produce 27.9 kilogram of iron. So in the B equation, we're looking for the mass of iron 3 oxide. So move. So we have the equation again. You see the equation mark now is on iron 3 oxide, Fe2O3, because is what we're looking for. Why it was made bold and then the equation mark on it. Then we connect it to iron. Because in this time they gave us the mass of iron. So connect, the iron is the known, while the iron 3 oxide is the unknown. Mass of iron is 27.9 kg given to you in the equation. But in chemistry, we work with grams because the molar mass is expressed in grams. So convert the mass to in kilogram to gram by dividing to 7.9 by 1000. When we divide it, we have 0.0279 grams, converting to 7.9 to grams. Then iron, atomic mass of iron is a metal, is monatomic. So that the atomic mass is 56. 1 mole of a metal is equal to its atomic mass. We're looking for the mass of iron oxide. We need to find its molar mass also. We calculate its molar mass by using that formula. The expression there. The atomic mass of iron is 56, but there are 2 atoms, multiplied by 2. The atomic mass of oxygen is 16. There are 3 atoms there, multiplied by 3. So when you solve this, you have 160 gram per mole. That is 112 plus 48. Of course, I've been done in the first example, first question. So we now connect the 2 substances. In the balance, we will connect iron to iron trioxide. 2 moles, start from the known, 2 moles of iron equivalent to 1 mole of iron trioxide. So let's go to the solution. So connecting iron to iron oxide in the balance equation, 2 moles of iron to 1 mole of iron trioxide. We'll now convert the mole to masses. How to convert mole to masses? We replace the mole with the molar mass. The atomic mass of iron, being a monatomic element, is 56, being a metal. So the 1 mole of a metal is equal to its relative atomic mass. To replace, so since they have 2 moles, they now have 2 times 56. That'll give you 112 grams of iron. And 1 mole of a compound, this iron trioxide is a compound, is equal to the molar mass, which is 160. So replace the 1 mole with 160 grams. You now have 160 grams of iron trioxide. So we have 112 grams of iron equivalent to 160 grams of iron trioxide. Therefore, 0.0279 grams, that is the mass of iron in the equation, will now be equivalent to 0.0279 times 160 over 112, and that will give us 0.0399 gram of iron trioxide. But the question asks us to find how many kilograms of iron trioxide. But we have to work in grams since our molar masses are in grams. So that will convert that to 7.9 initially to 0.0279 grams. We didn't use kilogram to solve it. But the question says how many kilograms of iron trioxide. So we have to convert the final answer, the mass of iron trioxide, in grams to kilogram by multiplying by 1000. Since 1000 grams make 1 kilogram. So now have 0.0399 times 1000, giving us 39.9 kilogram of iron trioxide required. Now exercise 7 says, consider the reaction between calcium carbonate and HCl, giving us calcium chloride, water, and CO2. When they say calculate the mass of calcium chloride obtained when 25 grams of calcium triazocarbonate 4 reacts with excess hydrochloric acid. So they gave us the molar mass of calcium carbonate given to us as 100 directly, so we don't have to calculate it. The molar mass of calcium chloride given to us as 111. So what are we looking for? We're looking for the mass of calcium chloride. That is the unknown. And which substance was given to us? They gave us 25 grams of calcium triazocarbonate 4. This one is the known, CaCO3, while CaCl2 is the unknown. We're going to connect the two so you can see the solution. The two substances were made bold. The known calcium carbonate, the unknown calcium chloride, question mark on it. Mass of calcium carbonate given to you in the equation is 25.0 grams. The molar mass was given to us as 100, already in the bracket. The molar mass of calcium chloride is also given to us as 11111 gram per mole. So this one is a straightforward question. We're looking for the mass of calcium chloride. So work from the balance equation, connecting the known calcium carbonate to the unknown, which is calcium chloride. So in the balance equation, the mole ratio of the two is 1:1. 1 mole of calcium carbonate is equal to 1 mole of calcium chloride. So you can see that 1:1. So we'll go back. 1 mole of calcium carbonate equivalent to 1 mole of calcium chloride. And then a mole is equal to the molar mass. So 1 mole of calcium carbonate is equal to 100 grams of calcium carbonate, the molar mass. And 1 mole of calcium chloride also equal to 111 gram. That's the molar mass. So now say 100 grams of calcium carbonate is equal to 111 gram of calcium chloride. Therefore, 25 grams of calcium carbonate, which is the mass given the equation, will now produce 25 times 111 over 100 by proportion. We'll have 27.8 grams of calcium chloride produced. We'll now go to exercise 8. Exercise 8 says, calculate the volume of oxygen gas at STP required to burn carbon to produce 8.8 grams of carbon dioxide. Atoms of carbon is oxygen is 16, carbon 12, and 1 mole of a gas, which is mvg, molar volume of gas at STP. That means 1 mole of a gas occupies this volume, 22.4 dN cube at STP. What are we looking for? Looking for oxygen. So oxygen is the unknown. What we're looking for, one of oxygen. And then what was given to us, they gave us the mass of carbon dioxide, CO2 is unknown. So, but first of all, what are the reactants? The volume of oxygen gas required to burn carbon. So the reactants are carbon and oxygen. To produce, the product is carbon dioxide. So we're going to react carbon and oxygen and then give carbon dioxide. Have to write the equation first. We say first we have to write a balanced equation for the reaction between carbon and oxygen. We have the equation, it's already balanced. Carbon plus oxygen giving us CO2. Then oxygen was made bold, CO2 was made bold. CO2 was made bold is the known. Look at it, the mass of CO2 was given to us as 8.8 grams. The mass is known. Then oxygen is question mark, it's an oxygen because it's unknown. We're looking for the volume of oxygen gas produced. So we're getting the mass of CO2 in the equation. We'll find the molar mass of CO2 by adding the atom mass of carbon 12 to oxygen 16. Multiply by 2 because there are 2 atoms of oxygen there. And that gives us 44 grams per mole. So we're looking for mass of oxygen. So the mass of oxygen, we'll now move on and say 1 mole of CO2. No, we don't. The question says we're asked to find the volume of oxygen, not mass. So that's error. Don't worry, we have to correct it here now. So 1 mole of CO2 give us 1 mole of oxygen according to the equation. Look at the equation. 1 mole of CO2 was produced by 1 mole of oxygen. So 1:1. We start from the known. We'll start from CO2, the known, and move to oxygen, that is the unknown. So let's go back to it. Where is it? Okay. CO2 1 mole, oxygen is there. We start from CO2 and move to oxygen. So let's go back. So we're going to change. We don't need the mass of oxygen since we're looking for the molar mass of, we're looking for the volume of oxygen. So this thing should not be, we don't need the molar mass of oxygen. So this 32 grams is not necessary here. The 32 grams should be changed to 22.4 because 1 mole of a gas is equal to 22.4 dN cube at STP. So we'll have to change that and get the right thing. So since we're asked to look for volume, so we are not looking for mass. So no need to calculate the mass of oxygen. We're asked to look for the volume of oxygen. So we'll have 1 mole or 44 grams of CO2, which is the molar mass of CO2, gave us 22.4 dN cube of oxygen. Therefore, 8.8 grams of CO2 given to us in the equation will be provided by 8.8 times 22.4. So let me make the correction here. Times 22.4 all over 44. So you solve and get your answer. Whatever answer you get, let's call the answer S. Will now be S dN cube of oxygen at STP. So when you solve that, you'll now get the mass of oxygen at STP. So, and that may probably give us around 5.6 dN cube, if I'm not mistaken. 5.6 dN cube of oxygen at STP. When this is solved, 5.6 dN cube. So let's look at the process again. We are not looking for, the question says, is that was an error? Volume of oxygen gas at STP that required to burn carbon. to give us 8.8 grams of carbon dioxide. The reactants are carbon and oxygen to use them to write the equation. Then we connect carbon dioxide because the mass was given to us to oxygen. So the mass of carbon dioxide is 8.8 grams. The molar mass of carbon dioxide is calculated as 44 gram per mole. We are not looking for the mass of oxygen as the mistake we made. We're looking for the volume of oxygen. So it's corrected. Volume of oxygen gas, not mass. So that's unknown. And then volume. And there's no need to find the molar mass of oxygen because we are not looking for the mass of oxygen. So the molar mass of oxygen is not relevant. We are not converting to mass. So we'll remove it. So we're looking for the volume of oxygen gas. So we'll connect CO2 to oxygen. For the balance equation, 1 mole of CO2 gave us 1 mole of oxygen. And 1 mole of CO2, the molar mass is 44. 44 grams of CO2 gave us, we'll now replace 1 mole of oxygen gas with 2.4 because 1 mole of every gas occupies this volume. Since we're looking for volume, so we have to make oxygen change it to volume, not mass. Then 8.8 gram of carbon dioxide, which is given to us in the equation. This 8 is given to you, 8.8 will now give us 8.8 times 22.4 over 44. And that probably gives us 5.6 dN cube of oxygen required to burn carbon. So that is the answer to this question. Okay, going to exercise 9, it says 20 grams of limestone will thermally decompose at STP as shown below. The limestone is calcium carbonate. We ask, calculate A, the number of moles of carbon dioxide produced at STP. B, the volume of carbon dioxide liberated at STP. They give us the molar mass of calcium carbonate as 100. They give us the molar volume of gas at STP at 22.4 dN cube. And they give us the Avogadro's constant as 6.02 times 10 to the power 23. So let's start with the first one, which says number of moles of CO2 produced at STP. Number of molecules, not moles. Number of molecules of CO2 produced at STP. Number of molecules. So we go to the balance equation. Okay, we say now work. Mass of calcium carbonate that reacted, that was decomposed, given to you in the equation is 20 grams. Molar mass of calcium carbonate is 100 grams per mole. It was given to you already, so you don't have to calculate it. It's 100 grams per mole. Number of molecules of CO2 is what we're looking for. So we'll go to the equation, write down the balance equation. They gave us this one, calcium carbonate, the mass given to us as 20 grams. That becomes the known substance. We're looking for number of molecules of CO2. So the question mark is on CO2, the unknown substance. So we'll connect calcium carbonate to CO2. So connecting the two of them for the balance equation, we'll now say 1 mole, the ratio is 1:1. 1 mole of calcium carbonate equivalent to 1 mole of CO2, and then 1 mole of a compound, the molar mass. So replace 1 mole of calcium carbonate with 100 grams of calcium carbonate equivalent to 1 mole of a gas occupied has this Avogadro's constant. 1 mole of a substance contains this number of molecules. So we'll now say 100 grams of calcium carbonate equivalent to 6.02 to the power 23 molecules of CO2. 1 mole of CO2 will contain this number of molecules. So according to Avogadro's number. So Avogadro's number represents the number of particles found in 1 mole of a substance. So 20 grams of the calcium carbonate will now contain 20 times 6.02 times 23 all over 100. By proportion, work it out. We'll now have 1.20 times 23 molecules of CO2. Going to question B. Question B says we should find volume of CO2 liberated at STP. So for question B, we'll go back to the equation. Now we're looking for CO2. So I have question mark on CO2, and then calcium carbonate, the mass was given to you already, 20 grams, given to you in the equation. You're going to connect the known calcium carbonate to the unknown, which is CO2. Then the mass of calcium carbonate is given to us already in the equation, as mentioned before, 20 grams. The molar mass of calcium carbonate is given to us 100 grams. Then connecting the calcium carbonate to CO2, ratio, number of moles, stoichiometric ratio of the moles is 1 mole of carbonate to calcium carbonate to 1 mole of CO2. So we'll connect them from the equation. We'll now say 1 mole of calcium carbonate gave us 1 mole of CO2. Then changing the 1 mole of, because we know that 1 mole of a compound is equal to the molar mass. So changing 1 mole of calcium carbonate to mass, that's replacing the 1 mole with molar mass, say 100 grams of calcium carbonate. Then CO2, change the 1 mole to volume. Since we're looking for volume, not mass, when I change 1 mole of CO2 to 22.4 dN cube, because 1 mole of a gas occupies this volume at STP 22.4. So 100 grams of carbonate gave us 2.4 dN of CO2. Therefore, 20 grams of the carbonate, which is given to you in the equation, 20 grams is the mass of the carbonate that is reacting, given to you in the equation, will now give us 20 times 2.4 over 100, and that gives us 44.8 grams of 4.48 dN cube of CO2. 4.48 dN cube of CO2 as answer. Exercise 10 says an ostrich egg shell containing some marble chips were treated with 250 cm cube of 0.10 molar HCl solution until effervescence stopped. Calculate the mass of marble chip in the egg shell. 2. Mass of calcium chloride produced. 3. Volume of CO2 liberated at STP. And they gave you the amount of calcium is 14, in bracket, chlorine 35.5, and then the molar volume of gas at STP as 22.4 dN. That's the volume applied by 1 mole of a gas at STP. Now, if you look at the question again, the ostrich egg shell containing some marble chip. Marble is nothing but calcium carbonate. Calcium carbonate can exist naturally as marble, can also exist naturally as limestone, can also exist as chalk. So that is calcium carbonate. So marble there represents calcium carbonate. So the reactant in the egg shell is calcium carbonate. What did it react with? It reacted with HCl acid. So we need to write the equation for the reaction. So solution, we need a balanced equation for the reaction between marble and acid. So we have the equation here written: calcium carbonate representing the marble in the egg plus HCl giving us calcium chloride, water, and CO2. I will make sure that the equation is balanced. Then from question 1 says we should find the mass of marble in the egg shell. The marble in the egg shell is nothing but the mass of the calcium carbonate. That's why I have question mark on calcium carbonate. We'll connect the calcium carbonate to HCl. Why HCl? Because we are given the volume of HCl, we're given its concentration. So we'll know the quantity of HCl that's reacting. So we don't know, we're looking for that of calcium carbonate. So our connection will be between these two substances. So we'll have to find, since we have volume and concentration, how to find number of moles of HCl using the formula N equal to CV. Number of moles is concentration times volume. But we'll divide by 1000 because of the volume there is in Cn cubed. So 1000 underneath, it will be required to convert the Cn cube to Dn cube. So if we use N is equal to CV, that means N equal to CV work out if the volume is in Dn cube, decimeter cube or liters, because 1 Dn cube is equal to 1 liter. But if the volume is in centimeter cube, you need to divide by 1000 so that you can convert the volume to Dn cube. So making substitution with the values given to you, 0.10 m, capital M means mole per Dn cube. So 0.1 times 250 over 1000, that gives you 0.025 mole of HCl. So we'll now connect from the balance equation. The balance equation, we're connecting the known HCl to the known calcium carbonate. That means 2 moles of HCl to 1 mole of the marble, which is calcium carbonate. So we'll now have 2 moles of HCl to 1 mole of calcium carbonate. You see, then 0.025 mole of HCl, which is the reacting mole of HCl calculated. 0.025 mole of HCl will now give us 0.025 times 1 over 2. So 2 is missing. It should be divided by 2, and that will give us 0.0125 mole of calcium carbonate. So that should be 2 under 0.025 times 1. That should be 2. By proportion, it should be 0.025 times 1 all over 2. So 2 is missing there. So don't forget to imply it. So that should be 2 under this expression. So 2 should be under it. So although the answer is correct, it's an omission. So we have 0.0125 mole of the marble or calcium carbonate. Then the molar mass of calcium carbonate is calculated. calcium is 40, carbon is 12, adding them together, then oxygen is 16. Multiply by 3 because of 3 atoms, that gives you 100 grams per mole. So we need to convert that 0.0125 of the marble to mass, since we're looking for the mass of the marble in the eggshell. So we use mass equal to mole times molar mass, that is 0.125, 0.0125, not 0.1, 0.0125. Let me make the correction. 0.0125. Let's correct it. 0.0125 times 100, and that will give us 1.25 grams of limestone. 1.25 grams of limestone or marble in the eggshell. So having done that, the next question says we should find the mass of calcium chloride produced. Now this time around, our question mark is on calcium chloride, the unknown. Okay, so and then we connect. Is an error? The known substance is HCl. We connect HCl, the known, to calcium chloride, the unknown. So you see that statement, connecting HCl to calcium chloride in the balance equation. Why do we use HCl? Because already we have calculated the number of moles of HCl using the concentration of the volume. But this time around, we're looking for calcium chloride. So now connecting HCl to calcium chloride in the balance equation, we now have 2 moles of HCl to 1 mole of calcium chloride. So 2 moles of HCl to 1 mole of calcium chloride. Therefore, 0.025 mole of HCl. 0.025 have been calculated before of HCl. Look at it here. No, HCl is 0.025, yes, mole, using CV over 1000. So that's the number of moles of HCl. So 0.025 mole of HCl will now give you 0.025 times 1 over 2, and that will give us 0.0125 mole of calcium chloride. So since we're looking for the mass of calcium chloride, we have to convert this mole to mass. The molar mass of calcium chloride given to us as 111 gram per mole. You can calculate it. It's already given to you, I think, in the question. Then, by using atoms of calcium as 40, chlorine at 5.5 times 2, 71 plus 40, that is 111 gram per mole. So the mass of calcium chloride is mole times molar mass, which is 0.0125 or 10 above times 111. So 0.0, correct it, 0.0125 times 111. That gives us 2.78 grams of calcium chloride produced in the reaction. The next question says we should find the volume of carbon dioxide liberated. So CO2 is unknown, question mark on it, we're looking for it. And then HCl, whose number of moles have been calculated in question I, is the known. So we connect HCl to CO2. So it's connecting HCl to CO2 in balance equation. We say 2 moles of HCl produce 1 mole of CO2, as you can see in the statement. 2 moles of HCl gave you 1 mole of CO2. 2 moles of HCl gave us, you know that 1 mole of a gas is 22.4, gave us 2.4 dN cube of CO2. Therefore, 0.025 mole of HCl, which is the number of moles of HCl, 0.025 mole of HCl will now give us 0.025 times 22.4 over 2. Should be divided by 2. The 2 is missing. By proportion, there should be 2 under this. 0.025 times 22.4 over 2. We solve and give the final answer as 0.280 dN cube or 280 dN cube. So there should be 2 underneath. Let's put it there. There should be 2 under this expression over 2. So that should be 2 under it. Okay, that is right. That is right. Okay. So that is the right thing. So we have it. So there should be 2 under the expression. By proportion, have to do the right thing. So that's the way it should be. 0.025 times 22.4 all over 2. And that'll give us around 0.280 dn cube of gas. You can convert to cn cube. But multiplying 0.280 by 1000, that gives you 280 cn cube of carbon 4 oxide obtained at STP. Now going to exercise 11. Exercise 11 says calculate the volume of hydrogen sulfide required at STP to precipitate 11.45 grams of lead-2 sulfide according to the equation below. Calculate the volume of hydrogen sulfide required at STP to precipitate 11.45 grams of lead-2 sulfide according to the equation below. So we're looking for volume of hydrogen sulfide. So hydrogen sulfide is unknown here. We're giving 11.45 grams of lead-2 sulfide with the known substance. So move on. So that equation, lead nitrate with hydrogen sulfide giving us lead sulfide and HNO3. And we're giving the atomic mass of lead as 207, nitrogen as 14, oxygen 16, sulfur 32. Then the molar volume of gas at SCP at 22.4 dN3. So let's go to the solution. So what are we looking for? We're looking for volume of hydrogen sulfide. So that is why hydrogen sulfide was made bold, and the question mark is on it. And then lead sulfide is also made bold because the mass of lead sulfide precipitate is given to us as 11.45 grams. So we're going to connect hydrogen sulfide. We're going to connect lead sulfide to hydrogen sulfide. So now go ahead to find the molecular mass of lead sulfide using the atomic mass of lead as 207 and sulfur as 32. So 207 plus 32 gives us 239 grams per mole, which is the molar mass of lead sulfide. So we are looking for the volume of hydrogen sulfide. So we go to the equation and connect the known substance, lead sulfide, whose mass is 11.45 given to us, to the unknown, which is hydrogen sulfide. So in the equation we have 1 mole. Each of them is 1 mole. So now I have connecting lead sulfide to hydrogen sulfide in the balance equation. 1 mole of lead sulfide gave us 1 mole of hydrogen sulfide. They will now change the mole to mass. 1 mole of the compound is equal to the molar mass. So we change 1 mole of lead sulfide to 239 grams of lead sulfide with the molar mass. Now we now change 1 mole of hydrogen sulfide to the molar volume, since we're looking for volume. So we're now looking for mass. We change 1 mole of hydrogen sulfide to 22.4 dN cube of hydrogen sulfide. So 239 grams of lead sulfide equivalent to 22.4 dN cube of hydrogen sulfide. Therefore, 11.45 grams of lead sulfide, which is the mass of lead sulfide given to us in the equation. 11.45 grams is already provided. The mass of lead sulfide produced. Okay. So therefore, 11.45 grams of lead sulfide will be provided by 11.45 by times 2.4 all over 239. That is solving by proportion. I will now have 1.07 dN cube of hydrogen sulfide. So we have come to the end of the mass volume relationship. So subscribe to this channel.